Okay, so yeah, I believe this is now live. So yeah, hello, hello everyone, and yes, today we're gonna be doing a bit of asset and base equilibrium stuffs, practice problems, and yes, by the way, these problems comes from the practice problem K of 3.091 of MITOCW. You guys can, you guys can go ahead and just check them out. And yes, last time I made a bit of a mistake. Is that yeah, NaHCO3 is actually a salt. It is in fact a salt n- known as sodium bicarbonate. So yeah, this thing should be converted into salt, and then after that, for the rest, I believe it is already correct, except for one of the things. Let me go ahead and just try to find it. 2.57. That's correct. Yep, weaker bond, stronger acid. And yeah, this guy here. This guy here was the one that just made me stuck, but yeah, I now have know how to how to how to actually solve this question. So yeah, basically this thing here, s- sodium lactate, add that to water, H2O. This would this would result to Na plus, and and this sodium, no, sorry. So yes, basically sodium lactate plus water would result into the sodium ion plus the lactic acid plus again with the hydroxide minus. And so with this, you can actually just find out what the thing is. This thing here is Kb, and so the terms would be Na plus. Whoops, I'm so sorry about that. So yeah, it is Na plus with that CH3COOH, which is lactic acid, and then NaCH3CHOHCOO, which is sodium lactate. And then from this thing here, we don't need to actually to divide it by H2O. In fact, actually in here we need OH minus. But then we don't need this guy here because this guy here is actually a salt. So yeah, we don't really need to care a lot. But yeah, sometimes oh, you know what? Let's just actually just put that there because I think I still need it. So yeah. So yeah, let's just do that. And then let me just go ahead and just open up this other side here. Um, yep, there we go. So yeah. So yeah, the first thing that we do is that we have actually discovered this thing, and then so now we just actually need to find out what is the O8. No, sorry. What what can we do with this formula? Well, yes, basically what I realized is that lactic acid or Ka here of lactic acid is basically this thing basically means this. CH3 CHOHCOOH, that's lactic acid, would dissociate into CH3CHOHCOO minus plus H plus. So yeah, let me just put that guy there. And yes, these two are actually aquifers. And so by the way, that actually that CH3CHOHCOO, the molarity of that must equal to the molarity of CH3CHOHCOO minus. So yeah. So basically this Na here is not really required because like yeah, because the molarity will be the same, and then theoretically and then also theoretically the Kb should be the same. So yeah, that's basically the theory. like yeah, it's like a little bit of theory as well. So yeah, we don't really need to include the Na plus because like yeah, if we put it down there, it would include NaOH or yes, Na plus, but yeah, I'm just too lazy to do that. But yes, at the bottom side you can actually just put Na plus CH3, CHOH, COOH plus water again, and then yeah, and then it would turn to something else. And so this Ka of 1.38 times 10 to negative 4, which is found just by finding the 10 to the power of negative 3.86. And so what the Ka really means here is basically the CH3, CHOH, COO minus. That's lactic acid, the concentration of that. There we go. I'll multiply that by the concentration of H plus, divide the thing by CH3, CHOH, COOH. That's lactic acid. And then what I realize here is that when you actually just do this, um, when you just actually just try to calculate Ka times Kb, which is basically Kw, you would get that it's actually H plus and OH minus. So yeah, it is just basically Kw. So that's Ka times Kb. And so what you'll get is that what does Kb what is Kb's number? Well, all you need to do is to just actually to put it inside your calculator, and you should get your answer. Which in this case I have already calculated it. It's 7.246 times 10 to the power of negative 11. There. And this would equal to x squared divided by 0.24 minus x, because like yeah, we just basically just look at the graph at this point. So yeah, let me just go ahead and just move this guy there. Let me just include x there. Well, yes, actually we don't really need to use the x, but oh well. So yeah, that's minus x, but then yeah, it's water, so we don't really care. And so with this 0.24 minus x there, so yeah, this would basically mean that it's x squared divided the thing by 0.24 minus x, which we found that x would equal to um x would equal to 4.3 no sorry 4.17 times 10 to the power of negative 6. And that's basically our x here, as the x represents the H plus, the the CH3 CHOH COO minus, and also the change in CH3 CHOH COOH. So yeah, that's a very wordy word. So yeah, what we can now find is actually that yeah, no sorry, the x actually represents the OH minus. I'm so sorry about that. But yeah, the x represents the OH minus. And so when we actually calculate the OH minus, what you get is POH equals to the negative log of the answer, which would be 6 min no sorry, when you put it inside the calculator, it's 5.38. That means the pH here would be 14 minus 5.38. That would be 8.62. And yeah, that's basically how you actually solve this problem. Very good. Number 8 now. Calculate the pH of each solution. Um. So yeah, let me just go ahead and just look at that. Yep, there we go. So we want to calculate the amount of those. So yeah, the first thing that I see here is that yeah, you can just go ahead and just see the dissociation is that H plus would result to H plus and a Cl minus. And so with this you can actually just know that actually that yeah, this thing would fully dissociate because it is a strong acid. And so therefore if we have like 6.09 molars of those, that would mean that this would this would theoretically fully dissociate, as the rest would be like yeah, basically they just gained 6.09 as well, molars. By the way, it's molars. And so with this, we actually found out that yeah, the amount the amount of H plus, no, sorry, the molar, sorry, the concentration of H plus would equal to 6.09 molars. Oh wait, no, sorry. But before that, you need to actually to know about the volume as well. Because like yeah, basically to calculate this, you need to first just to make sure that the volume is actually just to make sure that the volume for all of them is actually constant. So yeah. So yeah, I forgot to actually to mention that, but yeah. Instead, I just tried to calculate this, which is incorrect. So yeah, we just first try to find the amount of HCl in moles, and that's 6.09. Multiply that by 25 milliliters, but yeah, you need to transfer the milliliters into liters first. That would mean that it would be 0.025. So putting it inside your calculator, you would get 6.09 multiplied by 0.025. That would be 0.15225 moles. And so with this, if you want to calculate the real concentration of HCl, this would equal to, so so yes, all you need to do is to just to divide the number that you got, the answer that you got, you divide it by the total volume, which is 125. And what you'll get is actually 0.001218 molars. And yes, by the way, with this graph, actually, I should have actually just written this back down. Because, like, yeah, when you have, like, X of those, this thing this thing fully dissociates into H plus and Cl minus. There we go. And so the amount would be the same as the as the initial. So yeah, this would be the concentration of H plus. And so all you need to do is to just to calculate the pH, and this would equal to the negative log of the answer. Negative log of the answer. That would be 2.914 molars. Yeah, moles. Yeah. Yeah. Yeah, I guess it's correct. But yes, I will later just need to recheck it because yeah, I'm now just doing some more rechecking. So yeah, just to make sure that we are not actually making any mistakes, which I did make a mistake, which is I just multiply it by 125. Well, it should be 0.125 because we are talking about sorry, because we are actually talking a little bit on oh wait, because like yeah, last time we actually just divided with liters, so now we just divide it again by liters. And so this would actually be 1.218. And so with this, the pH is negative 0.085. No, 0.86. Yeah. And then you might say, well, yes, the molarity. No, sorry. The pH is negative. Is that correct? And the answer is yes. The pH the the pH is actually below zero, which might shock some people, but yes, obviously you can get pH more than zero. But yes, it is pretty rare. And then because of this guy having 6.09 molars, means that yeah, it has like a lot. It has a very high concentration of HCl. And so yeah, that's basically the first answer, which is the part A. For part B, it is the same thing that yeah, NaOH would fully dissociates into Na plus and NOH minus, which when you actually just calculate it, the sum would be this. No, sorry, the concentration would be the same for NaOH and for the OH minus. But yeah, let's just first actually find out how many NaOH do we have here in moles. So yeah, 2.555, multiply that by 0.005. Let's go and do that. No, sorry, 2.555, multiply that by 0.005. That's 0.012775 moles. And so the real concentration of NaOH would equal to, well yeah, this is the real one. So yeah, it's just 5 plus 75, that's 80 milliliters. That means that all you need to do is to divide the answer by 0.8. You'll get 0.0159. 6875 molars. So this means that, yeah, this means that the concentration of OH minus, no sorry, the POH, because like this thing is, because this thing here is actually the concentration of OH minus. So, oh wait, no, sorry, my bad. This thing should be 0.08. Because like, yeah, that's 8, yeah, yeah. That's correct, it's 0.08. And so this would mean that, yeah, uh, the, like, yeah, the concentration is correct, yeah. So this would mean that the POH would be the negative log of the answer. Negative log of the answer that you got there, which is 0.7, no, 0.8. That is pretty close. And so for the pH, you'll get is 14 minus that number, which is 13.2. And that's the pH of our NaOH. So yeah, it's pretty simple. So yeah, let me just go ahead and just see that. Okay. So let's go to the next one here, number 9. Salicylic acid is used in the synthesis of as acetyl salicylic acid or aspirin. 1 gram dissolves in 460 milliliters of water to create a saturated solution with a pH of 2.40. What is the Ka of salicylic acid? Okay, so yes, probably if you are at high school, you know the formula of the square root of Ka multiplied that by the Ca. But unfortunately for this, you don't have anything of those. Inst instead here it, but yeah, instead in the college level, you just actually just try to find it straight away. So yeah, basically, uh, so yeah, you just first actually just try to find what is the what do you call it? Bleh. 1 gram dissolves in 460 milliliters of water to create a saturated. So yeah, I believe that yeah, this guy actually talks about salicylic acid. So yeah, what's salicylic acid? Salicylic acid is, let's just actually just Google that. But yes, there's like a bit of a cycle of benzene, I believe, because yeah, it's because it's silic, which in this case it's true. So yeah, is there a better way to write it? Yeah, there is. So yes, the better way for you to write it is HOC6H4COOH. So yeah, this thing here is the benzene part, and then yeah, that guy is the one that actually just drops out to create that um basic solution. So we can just put that thing here. So we first need to try to find how many moles are there in 1 gram of salicylic acid. The way for you to do this is that you can actually just look up your periodic table. And so the H here is 1, but then we have 6, Oh yeah, we have 6. So we got 6 hydrogens. Add them up by 16 times 3. That's 48. So that's 54. Add the thing by 7. That's 84. So that would be 138, I believe. And wait, no, sorry. 84 plus 48. That's 102. Plus 6. That's 108. It seems off, I guess. Uh, yeah. Yeah, it's very off. So yeah. H is 1. So yeah, that would be 6. C, that's 12. So that means that we have 84 of those. 84, and then you add them up by 48. Oh yeah, 84 plus 48, that's 132. Plus the 6, that's 138 grams per mole. So we can just go ahead and just write them up there. 138 grams per mole. So how many moles are there in 1 gram of salicylic acid? Um, all you need to do is to divide 1 gram by 138, which I will do just by putting it inside my calculator, because obviously the calculator is the most powerful thing. Let's see. 1 divided by 138. This would be 0.0072 moles of salicylic acid. And so, if it dissolves in water with that many. Okay. So yeah, when it actually just dissolves into water, I normally just ignore the volume of the salicylic acid itself. So yeah, that's 0.0072 divided by 460 should give you the molarity. Divide the thing by 460. There we go. And what you get is 1.565 times 10 to the power of negative 5 moles, no, molars. So yeah, that's the concentration of salicylic acid. Uh, and then, by the way, this guy would dissociate into HOC6H4COO minus plus H plus. And so this would, and so with this, um, so this would mean that, yeah, you need to actually go ahead and just subtract the thing by x for this one, because this guy is at equilibrium. That should be x, and then for the H3O plus, that would be plus x. So, I need to get my calculator, unfortunately. Um, Let me just go ahead and just get my calculator first, just to solve this problem. So yeah, I'll be right back in a bit. Okay, here we go. Okay, let me just configure this guy again. So yeah. So yeah, the first thing that we do is we just need to make sure that we got an equation that we know that Ka would equal to um the concentration of H plus, which is the one that we have. I'll multiply that by, oh wait, oh yeah, yeah, it's correct. Multiply that by the concentration of HOC6 H4 C6H4 COO minus, there we go. Divide the thing by the concentration of HOC6 H4 COOH. So yeah, we just need to actually just to replace this guy because like yeah. Let me just actually just Command X that. Paste that, there we go. So yeah, basically that, yeah. This part here should be at the top here, there we go. And so we just need to calculate that. Which is a very crazy number, to be fair. And so let's just actually just go and do that. So let me just go into my let me just go and change my calculator into the correct format. So yeah, it would be x squared. And then the thing would be shifted. So that's 1.565 minus x. You put it into onto the Ka side. Oh wait, no, sorry, my bad. Oh yeah, my bad. Because what you actually realize is this one thing, is that yeah, the x here has been, well yeah, basically you have already known the x. How? Because you know the pH of the solution. If you know the pH of the solution, you can just basically just calculate the thing. And yeah, which in this case we know what is the concentration of H plus here, which is 10, which is 10 to the power of 2.40, negative 2.4. What I got here is 3.98 molars. So yeah, you can just actually just put it inside your formula there. 3.98 there. No, sorry, 3.98. Multiply that by 10 to the power of negative 3, which equals to x. Which equals to x. So all we need to do is to try to find the Ka here. Ah, wow. So basically, we want this x here to be squared, answer squared, and then you divide the thing by the concentration of HOC6H4COOH, which in this case it would be 1 divided by the grams per mole. Let me just reformat that. Reformat that, yeah. That's 1 over 138, and then you divide the thing again by 0.46. Wait, did I? Oh, I didn't actually did that. So yeah, this thing should be. Oh yeah. So yeah, this guy here should be 0.1565. Yeah. Yeah, 0.0. So yeah, in fact that yeah, you are just actually just reducing this number by a tad bit. So yeah. It doesn't really matter a lot, I should say. But yeah, it still matters a bit. Oh wait, actually, let me just change that to answer first. Yeah, I knew it. This thing should be 1575. Because I just did too much rounding, so yeah. I'm so sorry about that. And so yeah, that one sorry, so that yeah, that guy, the molar, so yeah, that guy, subtract that by the answer. And so when you calculate the thing, you should get okay. So what I got here, Ka would equal to 1.346 molars. Sorry, multiply that by 10 to the power of negative 3. And so that's basically the constant. That's, yeah, that is the constant. So we have found what number 9 is. Let's see here. Uh, 30 minutes in. Okay, we are good so far. Okay, write an expression for each salt. Expression for KSP for each salt. So basically, what is KSP? It is basically the dissociation of salts. Oh, that's what I normally say that. It is always this. It is always about a dissociation for me. But yeah, according to my notes, that's the solubility. And basically, the solubility is basically a very simple thing for it to write. Is that KSP would equal to, for example, here Ag here is Ag plus multiplied by I minus. Because of the coefficients is 1, so yeah, it doesn't have anything. And then you divide the thing by AGI, which is a solid, so you don't really need to care. So that's for part A. For part B, that would equal to Ca2 plus and F minus but squared. For the third one here, lead Pb, that would be a lead 2 plus and then chlorine minus squared. And then lastly for D, KSP would equal to the concentration of of silver plus, wait, yeah, Ag is silver, so yeah, silver plus chromate, which is CrO4 2 minus squared. Oh wait, no, sorry, but yeah, I just put the square at the wrong place. So yeah, that's basically the expression for KSP. I don't know if it's correct or not. So yeah. So yeah, later if I do another live stream, yeah, I will just tell you which one that I have gotten wrong. Part 11 here. The common ion effect. Describe the effect of a common ion on the solubility of a salt. Is this effect similar to the common ion effect found in buffers? Explain your answer. So yeah, basically for me, uh, the common ion effect is basically when the ion actually just separates into two because of water actually just taking it, and so yeah, it just separates. That's basically the common ion effect. So yeah, it's just like the dissociation of um of ions. That's what I actually state. And then the second one, is this effect similar to the common ion effect found in buffers? Uh so yeah, buffers, it's basically salt. But where does the Na plus actually, they like, yeah, they actually dissociate. Yeah, so yeah, I would say like, yeah, because of the what because of the salt, no, because of the conjugate is 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 actually dissociated. And yeah, and yeah that's that's about my concept. But yeah, it doesn't mean that it's correct. So yeah, that's why. So that's why I'm gonna later just Google them up. For number 12, molar solubility of from KSP. Predict the molar solubility of each compound using the KSP values given. Okay, Let's first actually try to do this. That's actually lithium phosphate. That's Li plus. Uh, you need you need three Li pluses, and also PO4. Uh, oh, okay. I just somehow yawned. Huh. Predict the molar solubility. Uh, what is the molar solubility? Let me just actually check first the molar solubility. It's at molars, so yeah. I guess that it's just calculating the x. Yeah, because like what you try to find is yeah, for each compound. So yeah, basically for this here you need to actually to be careful. So yeah, let's just go ahead and just try to find this guy first. Uh, so like yeah, for example, if you have like one lithium phosphate, um, it would dissociate, and so this would result to 3x. And for the phosphate, that's an x. That's PO43 minus. Wow. Well, I'm not just yawning. So yeah. So when you have like x of those, so if you have x lithium phosphate, is what they call it. So yeah. So now, so now I just need to make sure to transform this into 2.37 times 10 to the power of negative 11 would equal to the lithium to the power of 3, that's 27x to the power of 4 because of the total stuff. And so you just need to calculate the number and we should get the answer. So yeah, let's do that. 2.37 times 10 to the power of negative 11 there. There we go, I've written that down. Divide the thing by 27. And then after that, I'm gonna take, let me just shift that 4 of the answer. And there we go. I found out what x is. X here would equal to 9.68. And so yeah, this thing would equal to the molar solubility of PO43 minus, which is basically the concentration of PO43 minus. So yeah, it's pretty simple. And so for the 3x, that would equal to 2.9 times 10 to the power of negative 3, which would equal to the concentration of lithium plus. There we go. So yeah, I actually forgot to put 10 to the power of negative 4 here. So yeah, that's for the first one. For the second one here, B. The so you need like calcium 2 plus, and then you add that by the IO3, which I don't know how to say, iodate. I don't know. I which is a 1 minus actually. Oh, because of my predictions. I know my well, actually it's true because of the bonding. So yeah. So yeah, somehow I have known about this guy. So yeah, it's pretty weird for me as well. So so this guy here would mean that if you put x of that there, that would mean that you should get x of that of calcium 2 plus, and you should get 2x of those. So this would mean that we would get 6.47 times 10 to the power negative 6, which would equal to 4. x to the power 3. So yeah, let's just go ahead and just put that to our calculator. 6.47 times 10 to the power of negative 6. Yeah. Divide the thing by 4. You take the cube root 3 of the answer. What you'll get is that the x here would equal to 0.01012 molars, which would equal to, for the Ca2 plus, and then you got 2x here, which would equal to 0.023, which would equal to the concentration of IO3 minus, and that's basically your, and yeah, that's for part B. Lastly, for part C, y of IO3, so yeah, y is 3 plus, and then you add them up by 3 of IO3 minus. And so yeah, this guy would actually have x of those if you just put x of that salt, which would mean that the concentration here, which is 1.12 times 10 to the power negative 11, no, negative 10, must equal to 27x to the power 4. So yeah, same thing. Same thing as the very top there. So yeah, we can just do that. 1.12 times 10 to the power negative 10 there, and then after that, we can just divide the thing by 27, and then after that you will take the I don't know, the 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 tesseract cube root, no, the the tesseract root of the answer. Like, yes, I'm just starting to come up with new names for to the power 4, because like, yeah, you have square, you got cube, and now yes, at this point I'm gonna be saying tesseract. So yeah, don't be confused with the shape. Yeah. So this would be 10 to the power negative 3. There we go. Which would equal to the concentration of y3 plus. And then for the 3x here, this would equal to, multiplied by 3, you would get 4.28. Multiply that by 10 to the power of negative 3, which would equal to the concentration of IO3 minus. And that's all of the molar solubility that we have. Great, great. So now number 13. In a saturated silver chromate solution, the molar solubility of chromate is 6.54 times 10 to the power of negative 5. What is KSP? First things first, I believe chromate is a 3 plus. Let's see, chromate. Chromate is CrO4 2 minus. So yeah, what you have here is actually Ag, silver, silver to chromate, which is CrO4. And so, in a saturated silver chromate solution, the molar solubility of chromate is 6.54 times 10 to the negative 5. So what's the KSP? So yeah, basically you can just express this, which is the Ag plus squared, because like, yeah, I'm not just doing this in a faster method. So yeah, I'm so sorry if something is actually a bit not understood, but yeah, you can actually just read them up. This would equal to, we can just assume that to be x. So yeah, we can say 2x. So it will be 4x cubed there. which would equal to that number. So yeah, let's just put that into our formula. 6.54 times 10 to the power negative 5. There we go. And then we divide the thing by 4. You'll take the cube root of the answer. You'll get... Oh wait, the KSP. Oh, okay. So yeah. So basically in here, what you got there is actually 4x squared. No, sorry, it's 2x squared. Multiply the thing by x. And then the x here is actually the molar solubility of chromate, which we already have. 6.54 times 10 to the negative 5. So all you need to do is to just actually... let me just take that thing. Let me just call that. That. You take the cube. Yeah, and then after that you multiply the thing by 4. What you'll get is actually the KSP, which would equal to 1.12 times 10 to the power of negative 12. And this is basically the KSP. We have finally found it. Good. So next one here. Will it precipitate? Silver nitrate eye drops were formerly administered to newborn infants to guard against eye infection contracted during birth. Although silver nitrate is highly water soluble, silver sulfate has a KSP of 1.20 times 10 to the negative 5 at 25 degrees Celsius. If you add 25 milliliters of 0.015 molars silver nitrate to 150 milliliters of 2.8 times 10 to the negative 3 molars of sodium sulfate, will you get a precipitate? If so, what will its mass be? Okay. So we are talking about mixing those two salts. I don't know how, but yeah, I believe the Na plus and the SO4 minus should actually, yeah. The Na plus and the SO4 minus should actually, they should just actually separate each other, because because they are at water, and then you have that silver nitrate there. Oh, will it get a precipitate? So if so, what will its mass be? The mass? Wait, what? The mass? I well, that's interesting. Unfortunately, I can actually think about this. Silver sulfate. Oh, okay. I guess the first move that I would do is to just actually to make this into a reaction. AgNO3 that would result into Ag plus NO3 minus, and then after that you got us Na2SO4, which would result into Na plus 2Na plus SO4 2 minus. And then after that, what I have here is actually the silver sulfate that we have, that AgSO4. This would actually separate into 2 Ag plus and SO4 2 minus. But then we know the KSP, so that means that we know what the reaction should be. Yeah, I think we can actually do that. So when we know what the KSP is, you can just actually just plug it into the formula. So KSP would equal to the concentration of Ag plus 2 to the power of 2. There we go. Multiply the thing by SO4 2 minus. We don't need to care about the coefficient. This would equal to that. So yeah, that would be 4x cubed. Yeah, because like yeah, x multiply that by 2x to the power of 2. That's 4x cubed. And so, let's see here. 1.2 times 10 to the power of negative 5 there. Divide the thing by 4. You take the cube root. You should get 0.1. So what I get is x would equal to 0.144. Oh. So it's just asking about what's the mass of the precipitated thing would be. And so if we actually just do that actually, I believe that we can actually just figure it out at this point. So yeah, that's basically the concentration of AgSO4. Silver nitrate is actually a very soluble thing, so yeah. uh if you actually just mix those two would actually react with one another. One of them is going to be sodium nitrate, which is something that could be stuffed. Um, if you add 25 milliliters of 0.015, uh, hum, 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 hum. So basically, for silver nitrate, we can actually just ignore that. But for silver sulfate, you can just add those two up. Yeah, just to form that thing. So yeah, we can. Just try that. There's nothing wrong with trying. So yeah, N2SO4 plus AgNO3 should result into Ag plus 2Na plus NO3 minus plus SO4 2 minus. Wait. Well, basically basically my goal is actually just to have this guy react. So if I add 2 there, that means that should have 2, that should have 2. This would mean that what I would get is actually Na2SO4 plus 2 silver nitrate and O3 would result into the combination of those, which would be Ag2SO4 plus 2Na plus 2NaNO3. And so the question is, which one would precipitate? Okay. So first things first, what I actually see is that the silver sulfate doesn't really need to be calculated. That's my first intuition. Actually, what we can actually do is we can just plug the numbers in. We can try Uh, Wait, but that's the amount of the thing that is soluted. Uh, yeah, yeah. Oh yeah, it should be the one that was actually soluted. Uh, but but it doesn't talk about the one that would precipitate. Um, According to my intuition, um, those two should those two should react, and then after that, what you get is the one that is going to the right is something that you can calculate. Those are for the one that that goes to the left should be calculatable. This would mean something. Uh, Unfortunately, I don't really know. Uh, hmm. That's silver nitrate and that's sodium. Actually, we can actually just try to plug the numbers in first. Let's see. Um, 2.8 times 10 to the power negative 3. Multiply the thing by 0.15. That's 4.2 times 10 to the power negative 4, okay? 4.2 times 10 to the power of negative 4. Um, and then for this guy, that's that's the amount of moles that we have. For that guy, that would be 0.015 multiply the thing by 0.025. That's 3.75 multiply the thing by 10 to the power of negative 4. Uh, I mean, they have like. Oh! Oh! I see it now. Yes, yes, yes. I see it now. Watch. Because of 37. Yeah, yeah, yeah. Yeah. Yeah, from this point, you can actually just see that actually that silver nitrate is highly water soluble, which means that you can actually just ignore the silver sulfate and instead actually just make sure that it would actually just react. You know what I mean? No, good. So basically, what I've just seen here is that yeah, this guy needs to be subtracted by that amount 3.75 times 10 to the power negative 4. Yes, yes. And so this would mean that the one that we put at the front here should be that number divided by 2, which is following the coefficient. That would be 1.875. Let's see. Let's just put that guy there. 1.875. Multiply the thing by 10 to the power negative 4. Yes. This thing should work. Let's see. So yeah, this thing would actually react with the same coefficient. Yeah, it should be. So yeah, instead for instead for the right side, it is the one that is actually forming. And so with this, I can now just calculate it. This this could be something very cool. What about sodium nitrate? Does sodium nit no, sorry, sodium sulfate. Um, it is not talked, but I don't think so. But yeah, for the silver nitrate, that's something that is probably highly soluble. So yeah, 4.2 subtract the thing by 1.875. That would equal to 2.325. 2.325 times 10 to the power of negative 4. That would be 0. This guy here would be the same as those. And then for the Ag2SO4, because I know what the KSP is, could I just actually use that? The amount of Ag, yeah. Yeah. You can, because like, yeah, you can actually just assume that it actually subtracts by X. Oh wait, but actually, huh. Mm, we can actually just assume that it would react on them all. Like, yeah, those all would actually react. So the KSP would be the amount that would actually precipitate, which is 0.144. Uh, it is if you go above the boundary, I believe. But yes, luckily we don't actually pass the boundary, which means that the K there would be a much more negative number, which in balance needs to add them up by something, I believe. Because like the K should be balanced. Uh, I think so. Yes, I think so. So yeah, the amount of sulfate should be the same as 0.144, or or at least that number. Because um okay. So yes, unfortunately I don't have any more time, but I believe that we are actually heading in the right direction here. For number 14, I believe that we are actually heading in the right direction, which means that yeah, we could just solve it later on. But yes, I just want to say thank you very much for you guys who have actually watched the stream. But yes, unfortunately that I need to go right now. But yes, I will be later just gonna be trying to find the correct way to just to solve this problem. So yeah, thank you very much, and I will see you guys on the next live work. See ya.